So in the last lecture, we talked about concentration for martingales, and I finished the class promising some applications of that theorem. And the first application, perhaps the most important one, is another very important theorem that is talking about concentration for functions of bounded increments. Bounded difference. So let's first start with a setup. We choose a family of spaces. So we have, for example, omega 1 until omega n, just a bunch of spaces. And we have a function f that goes from the product of all the spaces to the real line. So it's a function that it's looking at several coordinates and it's returning a real number. We're going to define what we mean by the difference in the coordinate I, or the oscillation of f in the coordinate y. And this is going to be a supremum over all x1 in delta 1, in omega 1, sorry, up to xn in omega n. And also pick a special yi in omega y, omega I. And the supremum is going to be of the difference between f of x1 xn. So we're just evaluating f in this vector here, but we're subtracting f where we just replaced the ith coordinate with y. So instead of having xi here, we have yi. The rest of all the coordinates, they're kept the same. So this, in an intuitive way, is how much f can oscillate with respect to the ith coordinate. So this is a simple definition, but it's a powerful one for what we're going to do next. So the theorem that I want to present, it's an application of the martingales concentration. It's due to McDiarmid, who's also the author of the lecture notes I'm recommending for this part of the course. So suppose that x1, x2, and xn, they are independent with xi belonging to omega I. So you don't even require them to be in the same space, they just have to be independent. Of course, they don't have to be identically distributed because they're not even necessarily in the same space. And we denote by x the vector of x1 up to xn. So what this theorem is going to give us is if we have a function f from the product as before to the real line, we'll get a concentration of f of x around its expectation. So the probability that this deviates by more than t is bounded by, again, it's an exponential concentration, as you might have guessed, because I told it's an application of the previous theorem. And here we have something very similar to the previous theorem. Instead, the only difference is that in the denominator we have the deltas. But by the way, we also had some type of delta in the previous theorem. It was this is delta f squared. Before we had bk minus ak squared. Here we have delta I of f. So this is the theorem. It's giving some interesting concentration for a function that is not, first of all, it's not a sum of x. X is not necessarily something that you can sum. The first space could be the space of fruits. The last space could be the space of countries. You cannot keep summing these things. It's just an arbitrary function. It's not a sum, and it's although we are supposing that the coordinates are ID, f can combine them in very strange ways. So now let's go to the proof of the theorem. So the proof is going to be a simple application of the martingale concentration, although we're going to make some trick here. So we start by putting the thing in the setup of a martingale. So we first define a filtration. So Fi is going to be sigma of x1 up to xi. So it looks like we are defining the canonical filtration, but we are not, because x is not our candidate for martingale. X is just a bunch of variables that are not even real. So this is not the canonical filtration, it's a special filtration. And then we define zi to be the expectation of f of x given fi. So this is clearly a filtration. This is increasing. And now you ask me, why is this a function in L1, right? If I want to take conditional expectations, I better start with an L1 function. So here it's an observation. We had either sum delta I of f is equal to infinity. So either the f oscillates infinitely in one coordinate, and then this theorem doesn't give you anything, just gives you that the probability is smaller or equal to 1, or f is bounded. Why? Because if all the coordinates of f, you fix one point, f of some x is in R, right? And now we can obtain f of any other point by modifying x just a finite number of times. So this is going to be smaller or equal than f of x plus the sum of delta i's of f. So we have this observation. Either it oscillates infinitely or it's a bounded function. So we have no problem defining this. And we saw that whenever we have a filtration and a random variable, this is a martingale. And it's a very special martingale. I talked about it. It's the martingale that constantly reveals you more information. And it's usually an interesting idea to try to come up with this exact martingale whenever you want a martingale and it's not obvious how to get it. You just look at more and more information over time. Now, what we want to do is to try to bound the increments of this martingale, zi minus zi minus 1. Why? Because this is a hypothesis that we had in our theorem about concentration of martingales. We needed these increments to be bounded. Now, the way to do this, so to bound the increments, we're gonna make a small trick. So remember that we have the random variables x1 up to xn, right? Sorry. We're gonna create a copy xn prime. So x1 prime, x2 prime, xn prime, which are just gonna be independent of the previous one. So this whole block has the same distribution of this whole block, and they are independent from each other. And now we can define xji to be, xi to be the vector that takes x1. It takes all of this except at the coordinate I. So until the coordinate I minus 1, it's exactly this. But at coordinate it replaces it with x prime. Not here. And then it keeps going until xn. So this is a small modification of our vector x, right? Remember, x was just this vector here. And this we are modifying x only at coordinate I. Why is this interesting? So let's calculate the difference zi minus zi minus 1. So this is the expectation of f of x given fi, minus the expectation given fi minus 1. Okay, the first term we can keep the same. And the second term, because everything is independent, we can replace this by xi, right? The only thing that we have is that, so this vector here has the same distribution as the vector x. And when we make this replacement, we now have one variable here that is independent of fi minus 1. So here, let's make a visualization. So here we have x1, here we have x I minus 1, xi prime, xi plus 1, and xn. So here, let's do this lower. So here we have fi minus 1, which knows all of this, right? This is the information that gives fi minus 1. What is outside is just a bunch of things that are independent of the first I minus 1 random variables. So it doesn't matter if this is x or xi. I'm just putting some independent things here. Now the difference, which is important, is that this xi prime is not used in the definition of fi, not fi minus 1. So for fi, this is also independent. The x is not independent of fi, but the xi prime is independent of fi. So here we can just replace xi. We can just replace fi minus 1 by fi. Because to the eyes of fi, this is also something independent. There is no difference between this expectation and this expectation. They are seeing the same thing. Some variables they know the same amount of variables, the first I minus 1 variables, and they don't know the others. The others are independent. So there's no difference between this and this. Now, also arrived here, we can join the two because it's the same sigma algebra we are conditioning on. And now we can take the absolute value which is in the end what we want to bound, right? And the absolute value of the conditional expectation is smaller or equal than the conditional expectation of the absolute value. And this, what's inside, is always small, always bounded by delta I. Delta I is the supremum that such a thing can occur when these two variables only change in the coordinate I. So indeed, delta I is the difference, you remember, bk minus ak that we had in the previous theorem. So this is the bound on the oscillation of the martingale. Now we are in position to finish the proof because we have a martingale, we know its increments are bounded, so we can just look at the relation of our martingale and these things here. So let's look at what the martingale concentration theorem gives us. The probability that Zn minus Z0 is bigger or equal to T is bounded by some exponential. Here we have exactly the sum of delta I squared. Now, what is Zn? Zn is the expectation of fx given everything, given all the information. So this is measurable, so just f of x. What is z0? Z0 is the expectation of f of x given no information whatsoever. So remember that it started with x1, not with x0. So there is no information whatsoever. This is independent of this, so this is just the expectation. So here we have f of x minus its expectation. And if you look at the theorem, this is exactly what we're proving. Just should have written f here. As usual, I forget f squared. So that's it. This is the proof of McDiarmid's theorem. And now we are finally giving a more practical application of the theorem. So this is actually a silly application. It's not a very elaborate one. I can tell you that in my research, I've used this theorem several times and it saved my life several times. But the applications I had in my work are too complicated for this small time. So this is more of a silly application, but it's a beautiful one. So I like it. Imagine that you have a matrix like this or a screen of n by n pixels. Okay, so these are just pixels like this. And in this screen, you're gonna paint every pixel at random. So they'll throw a coin, and if the coin turns out head, they'll be called black. If the coin turns out tails, it's gonna be called white. So this is nothing more than a collection xij for both I and j between 0 and between 1 and n, which is an IID collection. Let's say they are Bernoulli 1/2 to make life even simpler. So we have a simple picture like this. And what I want to do is to look for Mickey Mouses. So what's a Mickey Mouse? So we have a square here of size 4. I'm not very good at pixel art here, but let's do my best. So this is what I call Mickey Mouse. It's a pretty one. So it has several squares, and I want all of them to be black. If one of them is not black, I've not seen a Mickey Mouse, right? So I want all these squares to be black. And we are looking for Mickey Mouses in this random matrix. So we want to count how many times we see this picture here inside. So we could require that the boundary of the Mickey Mouse is white to give a lot of good contrast, but I'm not doing this here. I'm just saying, if I see a Mickey Mouse, if I see all this here, for example, then it's one Mickey Mouse. But it could be like, for example, in the middle of a lot of blacks here. So if everything is black, I see Mickey Mouses all over. So what's the precise definition? So this we have to put in some grid here. And this grid has 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6. So it's a 6 by 6 picture. And we are going to define f of x. So x is this collection to be the number of Mickey Mouses. So how do we define this properly? It's the sum over I from 1 to n minus 6, sum for j from 1 to n minus 6 again. So we are going from here up to here, from here up to here. And in the sum, we have an indicator that, so here is 0, 1, 1. So that the first square, so let's take this first square. This first square has coordinates 2 and 0. So we want xi plus 2, j plus 0 to be 1. We want to see a black spot when we shift everything by I and j. So this is the square that we are looking at. We want to see a black square here. We also want to see a black square in the I plus 3, j plus 0. So we have a product here. We also want to see in the xi plus 1, j plus 1. This will be this square here. And you keep going, right? I'm not going to do the whole thing. The last one is going to be I plus 6, j plus 6. Because this will correspond to this last square here. And we don't look at what happens here, for example. We don't know if it's colored, it's colored. If it's not, it's not. As I said, we could have required a beautiful frame around the Mickey Mouse or a beautiful boundary to increase the contrast. But in this application, we don't care. It's going to be the same calculation essentially. So this is f of x. And the first thing we try to do is calculate the expectation. Sorry, let me change colors. Expectation of f of x. So the shift doesn't change the distribution. So this is going to be just n minus 6 times n minus 6. This is the number of shifts we have. And then we have to see all of these ones. But how many of them there are? Let's count. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16, 20. Oh, good. Beautiful number. So you have here to pay 1/2 to the 20 to see all those ones. And you could have a p here, it also doesn't change. And you could have a 1 minus p here to the number of things that we want to be white. But this is the expectation of f. So you see that here the f is not a sum of ID random variables. Far from this. If you see a Mickey Mouse somewhere, you have strong indication that there are Mickey Mouses around it, because Mickey Mouses correlate positively. By those who have seen percolation theory, FKG inequality tells you exactly that. But we are not into the FKG inequality business. We just want to show a law of large numbers that as n goes to infinity, the number of Mickey Mouses is going to be of this order. So when we let n go to infinity, we could see what's 1 over n squared times f of x. So since the expectation is growing like n squared, we hope to see a law of large numbers around this scale, right? And we'd like to show that this converges to 1/2 to the 20. Although there is positive correlation of Mickey Mouses, like seeing a Mickey Mouse helps you seeing a Mickey Mouse, this cancels with the opposite thing, that's not seeing a Mickey Mouse correlates with not seeing a Mickey Mouse as well. So in the first order, we don't see any change in the law of large numbers. It's just as if every one of the shifts were independent for the law of large numbers. But more than this, we want a concentration. We want to estimate the probability that f of x is far from its expectation. And if we show a fast decay for this, we have proved this law of large numbers, right? Because if we divide this by n squared, the first term goes to 1. And if the concentration is strong enough, the probability that this is bigger or equal than epsilon n squared is going to be very summable over n. So it's not going to be, it's going to be summable, yeah. So this is not going to happen infinitely often. So f is a function that fits exactly McDiarmid's theorem setup. It's a function of several independent coordinates, these ones. We just have to see how it oscillates. So what's delta I of f? So there are several ways to bound this, right? One possible, very crude way is to say, if we shift in our grid, if we change the value of one of these squares from 0 to 1 or from 1 to 0, there are certain shifts of this frame here that can be influenced by the change. But how many of them there are? At most 6 squared. So here we are. We have a function of bounded oscillation, and we are looking at the probability that it deviates from its expectation. So it's e to the minus 2t squared over the sum of this, which is just n squared times 6 squared. Now the question is this good enough for a law of large numbers? Is the decay good enough? So you already get the concentration, but is the decay good enough? Okay, you just have to replace t by epsilon n squared, which is what would set us away from our law of large numbers here. If we make this replacement, we get a bound of the type exponential of minus 2 epsilon squared n to the 4 over 36 n squared. And we're very good to go. We still get a kind of Gaussian decay on n. It's perfectly summable. So I have just proved the law of large numbers and a concentration for the number of Mickey Mouse. As I said, this application is silly not only because it has Mickey Mouses on it, but because there are other ways to prove the same thing using different techniques. But what I tell you is that there are situations, at least that where I know only this theorem will save your skin. So this is a good theorem to keep in mind. It's very easy to memorize. Maybe you cannot memorize this term, this you can look up in the book, but it's very easy to memorize what it says in spirit, and it's very easy to make such a thing occur. You get to choose the function f, right? So you can choose a very convenient function f and apply this theorem. It's something I definitely recommend memorizing and using. I'll see you next class.